So, thanks for the introduction. I'm sure many people have heard me talk about LC3 before, so there's going to be some repetition in this, but hopefully trying to give some new insights on why this is an interesting innovation and what are the barriers we now face. So I always like to start with this slide to really emphasize that cement is not a carbon-intensive material. You know, the number of people who come to me and their open line is, what are we going to do with this carbon-intensive material? It is not. It's just because we use humongous amounts of cement and concrete. We use something like 30 billion tons of cementitious materials like concrete and mortars every year. And you can see in this figure at the top right that from an intrinsic point of view of CO2 per kilogram, they have some of the lowest emissions of all materials. And this is the problem because we already have a low environmental impact and we have low cost, and this means it's really tough to do better. So I kind of thought about some innovations which stand out from the last 40 years. We've moved to high-strength concrete. We've moved to self-placing concrete. We've introduced superplasticizers, which is certainly an incredible innovation. Now we see a lot about self-cleaning concrete, self-healing concrete. Do these really make sense? 90% of concrete is still this plain vanilla variety. So we need to come back and say, well, why do we use this Portland cement? And it basically comes down to the composition of the earth, that just 8 elements make up more than 98%. And then if we look at how these 8 elements work in the context of cement, well, you know, 101, how does cement work? Basically, you have this gray powder floating around in water. And first of all, the grains dissolve like sugar dissolves in your coffee, and then they precipitate these new hydrates. So you need to have a chemistry where you can have this dissolution and this precipitation. So going back to the composition of the earth, we basically see the alkalis are too soluble, the iron and magnesium are too insoluble, so we've got the opposite problem. We can see a very old concrete here that the iron is just stuck in the same place. And similar story with slag. These dark rims around your slag grains are because that's where the magnesium stays. So we can't make cements out of that, which takes us down to just 3 oxides. It's really important to go through this because so many people out there are convinced there's some other miracle solution that's going to come along and make the problem go away. And then if we come to that diagram, there's basically these 2 regions where we can produce cement. This region we call Portland cement, and this region we call calcium sulfur aluminates. There's been a lot of hype about calcium sulfur aluminates as a way to lower CO2 emissions because they do contain less calcium oxide, and when you're producing from limestone, less calcium oxide is less CO2. But the problem is you don't just need less calcium, you need a lot higher alumina compared to silica, which means you're confined to using something like bauxite, which is very sparsely distributed, and even if we used all the bauxite we produce today, we would not be able to fulfill much of the cement demand. So this basically means we're limited to Portland cement, and the big difference we see between the composition of the earth and the composition of Portland cement is this concentration of calcium. And, we're very kind of fortunate because nature's sort of done a lot of the work for us of concentrating that calcium in the form of limestone. So this is what is called the slow carbonate silicate cycle. You get weathering of these common rocks, and then they carbonate in the Earth's atmosphere, picking up CO2. The problem is this is quite a slow process because it does involve the fact that these rocks have all got to dissolve. So the advantages of limestone are a lot, but the problem is, of course, then you get back all the CO2 afterwards. And more important than that, we actually face quite a problem in many parts of the world because, we have these 2 regions where Portland cement was developed nearly 200 years ago, where we see that the limestone deposits are very nicely interspersed with clay deposits. Now, when we go to places like Africa, we've got a problem because we see these limestone deposits are very sparse. And that means many countries in Africa can't produce clinker. They have to import clinker. And that's becoming a big problem because now when we look at how the pattern of cement use is changing, we see this complete transformation which has occurred in my lifetime. So when I was 2 years old back here, 98% of cement was used in the global north. Around 1990, we had the advent of development in China, which has led to the fact that China is now producing something like 50% of our CO2. But now that's going down because, you know, they're using 3 times as much concrete per person as anybody else in the world. And the other developing countries like India, Latin America, Southeast Asia, and there should be Africa up here, and I never know why, I forgot to check it. That should be nicely in red up there, but somehow on this computer it's gone to white and blacked out. That's probably, you know, something symbolic that we always forget about Africa. So what can we do about this? Well, there's a lot of things we can do, some of which we've heard today. But I think we, you know, need to think a little bit about what doesn't make sense. And, you know, as I say, if something seems too good to be true, then it probably is too good to be true. And many roadmaps are still saying, well, we have to look for these breakthroughs. But when we consider that cement is a solid material, it has to come from the earth some way or another. And the idea of radical breakthroughs, I hope you now understand, having sort of this elementary course in earth geology and chemistry, that, you know, some of these ideas border on magical thinking or alchemy. And then we can't really shrink our houses. This is another obstacle we have because a lot of the gains we've made in the efficiency of producing cement, etc., has actually been wiped out by the people wanting to have larger houses to live in. And, you know, there's a lot of startups out there which are trying to deny this basic cycle here. You know, we use limestone to produce cement. It gives off CO2. It then hydrates, gives us all these nice solids, which gives us durable concrete. And it will recarbonate over time, but clearly the amount of CO2 that can be reabsorbed can never exceed the amount of CO2 that was given off. So there are a lot of claims of, you know, we can add calcium oxide, calcium hydroxide to concrete. It will absorb more CO2. It's kind of true, but only if this calcium oxide or calcium hydroxide came from uncarbonated sources would it have any net benefit. And we've just been looking at this, we've been studying this in detail for the past 2 or 3 years. And the problem is we've got very, very limited amounts of these materials. These are some of the figures here. I'm sorry I can't show you the much nicer figures, but because the paper's under review, I can't use those yet. But basically the end of story is this can contribute, it can be significant. We should recarbonate these materials, but it's going to be a very small amount. And then, you know, unlike the algae presentation we've just seen, some people say let's use this algae to sequester, to make calcium carbonate. And there are algae that can produce calcium carbonate. They were a big contribution to forming limestone in the first place. But again, you've got to give them a source of calcium, and that's what we're lacking. We're lacking sources of uncarbonated calcium. So all of this is kind of an introduction to say, well, you know, this is the analysis. There's no great miracle out there, but there's still a lot we can do with the very simple technology of blended cements or using SCMs in concrete, which we've known for many decades now. We can introduce limestone. This was done 30 years ago in Europe, and it's just being done in North America. I think you've got to move faster to catch up. You know, we've got to see more ambition here to really bring about CO2 reductions. And then we have fly ash, but this is, you know, horrible stuff that comes from burning coal, which is the number one thing we've got to stop. And slag, which is a very nice SCM, but unfortunately comes from this very CO2 intensive process of producing steel. And then what's new? Well, the only thing really that can change this equation are clays. Because clays are super abundant, they're available everywhere. And when you calcine them, that's to say you heat in the range 800 degrees, they become very reactive materials. So this figure shows the availability of SCMs compared to Portland cement. And here you see the big problem. You see, even today, the amount of slag is only 8% compared to the amount of cement. And this is pretty much all sold out. 95% of slag is already used in cement and concrete. So if you specify in a project to use a high volume of slag, you're just taking slag away from somebody else. And your project may have lower CO2, but somebody else's project has higher CO2. And on a worldwide level, we gain absolutely nothing. So we have a lot of limestone, but we know with the Portland limestone cements that above about 15%, we just get a dilution. So the great thing about LC3 was really the discovery we made quite a few years ago now, that we could have a synergetic reaction between the limestone and the clay. And this synergetic reaction allows us to go to high levels of substitution. So what we're doing here, we're replacing the more carbon-intensive clinker with a combination of calcite clay and limestone. The limestone has pretty much zero CO2 because it's not been through the cement kiln, and the calcite clay pretty low CO2 because it's calcined at a much lower temperature and there's no process emissions. But here, even with this 50% substitution, you can get the same performance as Portland cement within 7 days. And that's the secret, because you cannot do this with other SCMs. Fly ash is maybe catching up at some time after 28 days. You can't get the same early strength, and that's often a limitation on the substitution level for practical construction. So just to summarize briefly, we've got 50% less clinker, 40% less CO2, similar strength, and some properties like resistance to chloride and alkali silica reaction are very much improved. And why do we get this synergetic reaction? Because we're using clays that contain some kaolinite, which has this one-to-one layer structure with a layer of silica and a layer of alumina. And when you heat it up, this becomes disrupted. Both the silica can react in the pozzolanic reaction, and the alumina can react in this synergetic reaction with limestone to give us these products we call carboaluminate. They're actually there already in Portland limestone cements, but we've got somewhat more of them in these blends. And here we can compare the reaction of the calcined clays with slag and fly ash. At long ages, they're all about the same. The issue is that the calcined clays can deliver a lot more early, and from a practical construction point of view, this means you can use higher levels of replacement in practice. And if you work on the grinding a bit, you can even get the same strength at 1 day, as we showed in this experiment here, where we just took a cement, we just reground it, and we could get the same strength at 1 day. You've got a lot higher reactivity than things like uncalcined pozzolans. This shows an example of work we did comparing the pozzolan used in Chile, where they have quite a reactive pozzolan, but we could get the same performance with lower clinker contents by 40-45%. So things like fly ash and natural pozzolans can do a really good job of controlling things like alkali silica reaction, but it's really difficult to go to these high replacement levels you need to save CO2. So we do need kaolin in the clay, but these kaolinitic clays are very widely distributed. Everywhere you can see this kind of orangey color, you will have kaolinitic clays, and nicely they're really available in those countries where we need them to address this growth in demand for cement. Honestly, the issue of cement is not in North America or in Europe. It's in these countries where the growth is going to occur, and we need to get technologies that can be used there before these buildings have been built. After the buildings have been built, well, all the CO2 has been emitted. And we can measure the kaolin very easily by looking at the weight loss between 400 and 800. We see it correlates really clearly with the strength development, and the red bars show the reference for the reference Portland cement. So for at 7 and 28 days, we can get the same strength as the reference Portland cement with kaolinitic contents of around 30, 40, 50%, which are not used in other applications. People are often confusing the fact that we're talking about kaolinitic clays with metakaolin, which is a very expensive product and is used in many other applications. But often the kind of clays we can use in LC3 are found as waste from those other industries because the grading, the content of kaolinite is too low for those applications. We've got existing technologies ready to go today, which can do the calcination with emissions as low as 90 kilograms per ton. So that's about 1/10 of the emissions of clinker. And we've taken this to full scale, built houses out of it. There's already existing plants, such as this one in the Ivory Coast. And the importance of this one in the Ivory Coast was to demonstrate that you can control the color. Because many people say, well, people aren't going to buy red concretes. Well, if they don't want to buy red concretes, they don't have to buy red concretes, because as you see on the right here, you can turn the color gray with a very simple technology existing from the brick industry. So in terms of chloride resistance, it's much, much better. The black line is the reference Portland cement. The red are the mixtures with slag, which are better. The blue are the ones with fly ash, which are better still. But the purple ones at the left show you the dramatic reduction of chloride penetration you get with these materials. You have chloride penetration coefficients of diffusion coefficients about 10 times less than the Portland cement. Well, of course, if we use FRP rebar, we don't need to worry about that. But, if that's hopefully going to advance fast, but in the meantime, this can be very good for marine environments. And so what's the potential? Well, this is really the critical thing, because this graph here shows the average level of cement substitutions in the last few years. And you can see for the last decade or so, there's really been no progress. And this is due to the limitations in amount of slag and fly ash. These figures are global figures. Most of the rest of the world already uses blended cements. I know in North America you like to add them at the concrete stage, but it's kind of basically the same thing. Now, if you remove this limitation, you can certainly imagine to go to a substitution level of 40% quite easily, which would represent about 400 million tons of CO2 per year. But if we're thinking, 2050, which is where we've got to be, you can at least double that, because, we are already exploring ways to go to higher clinker substitutions, which can come to something like 800 million tons of CO2 a year. And the good news is this can all be done even more cheaply than producing Portland cement. So the presentation from Brimstone said they aim to produce cement on the market at the same cost. Having read their patent, I would say good luck to them. But this here we can really show today is a technology where you can produce cement more cheaply. And I'm very pleased to say that it's now being taken up in all these countries around the world. So here we come to the crunch. What's the blockages? I mean, this is the problem. People say, we've got no time to do anything new. You're making money in the cement business is having a kiln that operates 24 hours a day, 8 days a week, something like 320 days per year. You don't have time to do trials, and the bonus of the person operating the cement plant does not depend on innovation. It depends on getting the product out the door. And this is one of the main obstacles. There's a real lack of ambition. We had a meeting on Friday, and one of the major cement producers said, well, we don't have to pay anything for CO2 in the US at the minute. Well, maybe you don't at the minute, but I think that's going to change quite fast. So I think you should start preparing for it. Then they say, well, we can't find the clays. Well, if you think back to that map I showed you, they are very abundantly distributed. It's just a question of looking for the right things. You will need some investment, but generally to increase the capacity by producing LC3, you'll need about 1/10 of the investment for putting in a new clinker line. And then again, it's a question of lack of awareness, because thinking about these developing countries, particularly in those parts of the world, the largest companies make up only a small part of the market. So, and then we have, of course, our favorite codes of standards. So our strategy has really been, the following. We decided not to try and make a commercial venture out of this, because what we wanted to do was get this technology into as many of the 3,000 plants around the world as we could. And the majors only own about 30% of these outside China. So we did focus first on the majors, because then if you can convince a big producer, then they've got maybe hundreds or even several hundred cement plants around the world, and then you can have a multiplication effect. And we also worked on the academic side of, convincing the academia this was a sound product. And now I'm very pleased to say, this is a snapshot of the publicly announced plants that are already being produced or already producing. There's many, many more that are not publicly announced. So where do we go now? Well, what we need to do is now we need to shift to the use stage. So, we have now some examples of people who have accepted to use LC3 in big buildings. This is now the challenge. We're talking about a blended cement. So the performance is really identical to cements based on slag and fly ash we've already been using for several decades. And of course, we have to realize this is only one part of the puzzle. We have to not only reduce the clinker in cement, reduce the cement in the concrete, reduce the concrete in the buildings, and use our buildings more efficiently. Because the kind of pattern we're seeing, these are the same levers that one of the other people showed. We can do all these things at the top. We can have all this reduction at comparatively low cost, or even negative cost. At the end of the day, we've got a small amount that's going to have to be dealt with by carbon capture and storage, but our interest is really to minimize that amount, because that is going to be the expensive step. So with that, I'd like to thank you for your attention and hope maybe we have still a bit of time for questions.